Hi and welcome to video 9 on our video series on linear equations and their graphs, and this is simultaneous equations solved by elimination. Here's a second algebraic method, simultaneous equations by elimination. Now I've got an example up here, but first we're going to go to our list that will outline how you might go through simultaneous equations by elimination. This list is going to seem a little bit abstract now, so it's worth having a look back at it after you've gone through some examples. But for now you can pause the video to have a closer look if you would like. Well, welcome back, and I hope that list was clear, but if not, I'm hoping that when I refer to it here, you'll see what's happening. So, we've got simultaneous equations by elimination. You can see my two equations here, and this is a classic situation where elimination is going to be really good. So I'll show you how this works. Firstly, I've got equation 1 and equation 2. As usual, we give them a name so we can refer to them. Now in this case, what I'm going to do is I'm going to eliminate the y variable by doing equation 2 minus equation 1. Now I could do equation 1 minus equation 2. It would work perfectly fine. I'll just get some negatives, and I'll try and avoid negatives where I can. But equation 2 minus equation 1 will mean that I've got, and this is going to be the long form, I'll do the short form later on, but it means that I've got 5x minus 2x. That comes from here. So think of it like you're subtracting something in the tens, hundreds, ones column, etc. And then I've got y minus y, and that's equal to 20 minus 11. And we've done this very specifically because our y minus y is going to be 0. And so naturally we have no y's left in the equation, and we're back in a situation where it's just x's and a number, and we can solve for x. So 5x minus 2x is equal to 3x, y minus y is 0, and 20 minus 11 is equal to 9, because we now divide by 3, and we get x equals 3. And we use that x equals 3 into either one of our equations. Unlike substitution though, we haven't already rearranged, which is a bit of a shame. But I'll go to equation number 1 now, and I get 2 times 3, because we know x is equal to 3, plus y equals 11. So 6 plus y equals 11. We subtract the 6, and we get y is equal to 5. So our solution here is y equals 5, x equals 3, and we should always conclude to make it clear to the marker. Now this has worked really nicely, and often I find students will say, I like this method better, and sometimes it really does work quite quickly. So it's a good method to know. Substitution does have some benefits. There's times where substitution will be easier, and there's times where elimination will be easier, and the best students will know when to pick which one. But also, the substitution method does lend into some other topics, where elimination, not so much. But that's fine, it's still a really good method to use. So let's have a look at another example. Okay, example 2 by elimination. So what we're going to do for elimination is subtract equations, right? Well, not quite in this case, because in this case we don't have the same number of y's, or in this case a's and b's. We've got 2 a's and 5 a's, so if you do a subtraction it doesn't eliminate. 3b and b, do a subtraction it doesn't eliminate. So we've got a bit more of a problem here, it doesn't really run as naturally. So then we think to ourselves, well, let's just multiply some equations out to try and make it work better. So 2 times y equals 5. Well, the answer is 2.5, but then I've got halves, so I don't really want to deal with that if I can avoid it. So I'll show you a technique for that situation in example 3. But for now, this 3b and b, well, they can be brought together by getting equation 2. So this is equation 1, this is equation 2, and multiplying it by 3. And that'll create a 3b situation. So let's do that now. What I'm going to do is I'm going to draw them both again. It's just a nice way to work it out and make it easier to see what you're doing. So 2a plus 3b equals 9, and then 5a becomes 15a because I'm multiplying the equation by 3, minus, and then 3b, and negative b becomes 3b, And then 48 becomes 144 because I'm multiplying it by 3. Everything in equation 2 has been multiplied by 3. Now last time we subtracted because we had y and y minus y is 0. This time though, I'm going to actually, I'll rename them 1 and 2 because they're kind of the same equation. I'm going to do 1 plus 2. I need to be careful and thoughtful about what's going to eliminate a variable. My a is obviously won't eliminate because I'll end up with 17a, but 3b plus negative 3b will be 0. So I'll come out with, and I add these together, I get 153. 17a equals 153. Now I've got the benefit of a calculator, so I just divide 3 by 17, and hopefully if you do this in your calculator, you'll come out with a equals 9. That's the elimination method. But I had to be a bit more clever about making sure my b's matched up before I could really do this elimination. Now I've got my a value, I need to put that back into one of my original equations. And I'm going to choose the first one, just because the 3b, it's got a 3 out the front, but it's not negative, and I'm just trying to avoid the negatives where I can. So in equation number 1, I put in a equals 9, so I get 2 times 9 plus 3b equals 9, gives me 18 plus 3b equals 9. I subtract 18 from both sides and I get 3b is equal to negative 9, and hence b is equal to negative 3. Let me write that down, subtract 18 and then divide by 3. There's my process, there's my final answer. Of course I substitute that, I'll write down my final answer, sorry. A equals 9, b equals negative 3. So there's our second example of using elimination, but in this case where we had to blow out one of our equations so that we had some comparative elimination opportunities. Well, here we are with our final elimination example. There's plenty of other examples on other resources, textbooks, etc. So definitely check them out, but here's my final example. Done that trick again. K and C are my two variables, and I've swapped them around. So I've got K and C and then C and then K. It's a little bit annoying. I've led with a negative, which is also a little bit annoying, but I'm here to be annoying so that you can learn how to solve these equations. So, looking at these equations, I can see a bit of an issue. The trick here is that I reckon a lot of students would come in and just go, oh, I'll add those and wipe out the 2 and the 2. But they're actually different variables, so you have to be careful. I've got 5c here and negative 2c there, and they don't line up very nicely, nor can I multiply the 2 by anything nice to get to the 5. I've also got 2 and 7, which is also a bit of a pain. So what I'm going to do is I'm going to do a swap on these two variables in my next line, but I'm also going to, after labelling them, 1 and 2, I'm going to recognise that my negative 2 and 5 are the smallest pair of numbers, 2 and 5, rather than 2 and 7, so it won't blow my numbers out as much, which is a good thing. I'm going to multiply this equation by 5 and this equation by 2. It's kind of like that old cross-multiplying technique in fractions, and it will mean that I get 10c here and I get negative 10c here, and then eliminations back in the table. So, let's do this. 1 times 2 becomes 4k plus 10c equals 16. And 2 times 5, and I'm going to swap as well, so 7k becomes 35k minus 10c equals negative 55. Pause there and check if you need to, but I've multiplied everything here by 2 and everything here by 5 and done a little swap as well. Now, because I've got 10c and negative 10c, I'm going to pop a little plus in there. And so I get, these cancel out, and I'm left with 39k is equal to negative 39. So negative 55 plus 16 is negative 39. Now I don't even need a calculator for this because I'm going to divide by by 39, so not negative 39, and I'll get k is equal to negative 1. So that's good. I've gone through that elimination process and here we are. And this is a hard one, and yet still it doesn't take that long. If you're methodical, you follow the rules, just make sure you're doing the same thing to both sides of an equation, and you might go down the wrong track that doesn't help, but as long as you're doing things mathematically correct, it won't go wrong. You can always redeem it. K equals negative 1, I'm going to put that into one of the equations. Quite like this top one with no negatives, so let's do that, and I get this. So into 1, I get 2 times negative 1 plus 5c equals 8. That gives me negative 2 plus 5c equals 8. I add 2 to both sides, cancelling out the negative 2, leaving me with 5c. 8 plus 2 is 10, and I divide by 2, and I get c is equal to, and by divide by 2, of course I mean divide by 5, c is equal to 2. So, my final solution is c equals 2, and k equals negative 1. And because it's the last example, let's j the r. That is justify the reasonableness. Now I've just gotten my c value, the last value I got from equation 1, so let's j the r in equation 2. So in equation 2, I've got negative 2c, c is 2, plus 7k, k is negative 1, that's equal to negative 4, plus negative 7, which is minus 7, which is equal to negative 11. And that matches my negative 11 here. So I've justified that this solution is reasonable and works in both equations. Anyway, that's simultaneous equations by elimination. All the best. Well, congratulations, you've made it to the end of substitution by elimination.